Hi, everyone. Happy Thanksgiving. I am waiting for my baguette dough to rise, so I thought I would come in here and record a math video about a problem I came up with a while back that I really like. So in case any of you guys didn't get to come to section this week, but you're curious maybe about some of these like weird, unusual problems I referenced, this is one of them. Okay, cool. My tablet's logged in, so I'm just going to share my whiteboard and we're going to go over how it works. So this has to do with fractals. And it's fractal that doesn't come up very often. It's related to a thing called the Koch snowflake, but it's a little different from it. So I call it the square Koch snowflake. And it looks a little bit like this. What you do is you start with a square, and we're going to say that square has side length 1. It's not super important, but we'll go with that. And then what you do to make it a fractal is you cut each of these 4 sides of the square into thirds, and on each of those thirds, you put another square. Okay, so then each of these would be side length 1/3. It's actually 1/3 all around. You know, even this, like I said, I'm dividing this whole line into 3, so it's 1/3 all around, but I'll just show it on a couple sides there. And then I want to continue this process again. Okay, so what I'm going to do is I'm just going to focus on one side of the shape. Okay, and then it's kind of symmetric from there. Because whatever I do here, I could mimic here and here and here. So I'll just show it for one so I don't have to draw a whole bunch. If you want to draw it out yourself, I recommend using grid paper, but I don't think Zoom has that function. Okay, so these little squares would look like this. They're actually touching at these points, interestingly enough. You could maybe figure out why if you drew it more precisely. Okay, and then so each of these tiny squares has side length 1/9, right? And we're going to imagine this whole thing as a solid shape. So it's like filled in, we'll say. Okay, so that's all filled in. There's some little gaps here, right? Because I didn't add squares there. So there are 2 little gaps. And then we would keep going, okay? And so you kind of have to use your imagination to think about what that means if I repeat it over here, repeat it over here, repeat it over here, and then continue to infinity. Okay. Fractals often come up in this context where you define some process and then repeatedly apply that process infinitely many times. And before calculus, you would think that's a weird concept. But now you can say, I'm really asking about the limit of this shape. It's another way to think of it. Okay. So what we want to find out, the interesting question is, what is the area of this infinite shape? Okay. So I don't want to spoil the surprise. I welcome you to work it out on your own. You don't actually need calculus for this. You could make sort of an intuitive kind of geometric argument. Actually, without knowing much geometry, you could make a kind of clever argument. There are really only 2 options. One is the area is infinite, right? Because we're continuing to infinity, and each time we're adding little chunks. So you might think, okay, grows and grows and grows and never stops growing. So the area is infinite. Option 2 is it's not infinite. Okay, it's some finite number. And I'm going to write out a quick argument why one of these is correct. Okay, so I encourage you to pause the video and think about which case is correct. So pause now if you want to. I'll wait a few seconds. Okay. The correct answer is it's finite. And not only that, but we can find the exact area. It's not going to be some weird decimal that never ends or some weird irrational number. It's going to be a nice answer. And let me make an argument quickly for why it's not going to be infinite. Okay, my argument goes something like this. As I continue this infinite process, let's do like one more stage here. Maybe I'll draw it in a different color other than red. Let's use black. So why not? As I continue this infinite process, and I add, in this case, I think it would be 25 little squares. Just drawing them as little bumps here. So count it out, convince yourself it's actually 25. The important thing is that these little sections here, well, actually I'll ignore that for now, but pay attention to those sections later. The real important thing is that the side lengths of the squares are shrinking really quickly. You might say exponentially quickly, but that would be incorrect. Yes, geometrically quickly might be the correct term. Doesn't matter. What does matter is I can bound this shape with another shape. Okay, it's not like these things are going to keep growing and I'll get squares out here and it'll go out to infinity. Instead, I could put a perimeter around this and I guarantee you it'll never bleed outside that perimeter. Okay, the perimeter ends up being something sort of like this. Okay, so it's just a line with slope 1 or -1 that starts at the corner of the original square we started with and then goes up to a point. I guarantee you we'll never go outside that as long as we're precise. I think some of mine probably did go outside, but it's not a big deal. We'll allow it. Okay. So in total, what happens then is this one does something similar. It goes up to a point here. This one does something similar, goes to a point here. Okay, and it's similar all around because it's nice and symmetric. And so we get a bounding shape. And so my claim next is that the blue area, which is the area of this snowflake, this sort of thing that we continue to infinity, the blue area is definitely less than or equal to the red area, where the red area is just that whole diamond. Okay, so maybe we can bound it. What is the red area now? Again, pause the video and think. It doesn't require any advanced math. It's just a tiny, tiny bit of geometry. Not even the geometry you're used to in school. It's not like anything super fancy. You don't need sines or cosines or any of that. So yeah, pause the video and then I will provide the answer. Okay, the answer is, well, I need to figure out the length of these red sides, right? That'll give me the area of this red square. I called it a diamond, but a diamond is just a square on its side. And it turns out this side length right here, say, is actually the same as the diameter of the original square. So that's the little bit of important geometry. That's the only fact you need. And then since we know the sides are length 1, you can just use the Pythagorean theorem. A squared plus b squared equals c squared. A and b are 1. So that's c squared equals 2. So this hypotenuse is square root of 2, which means the side is square root of 2. And the other side is square root of 2. All the sides are square root of 2. And so the area that we're talking about here is actually 2. Okay. So that is hopefully intuitive now, since I drew the picture out. But it should also be counterintuitive in the sense that I'm adding up infinitely many things and getting something that's less than or equal to 2. Okay. Maybe some of you guys have seen that before. I expect most of you have not. And it's a very counterintuitive thing. But I think presenting it in this geometric framework maybe helps you grasp it. Although maybe you're not convinced by my argument about the squares not bleeding outwards. Maybe you think if you go far enough, maybe they break outside of that square. So maybe work hard on some graph paper and convince yourself. But anyway, this is a deep fact that an infinite sum, a sum of infinitely many things, can be finite. That's just a deep fact of mathematics. Okay. So, and it's great. Okay, so like our blue area is less than or equal to 2, but what is it? Like, give me a number less than or equal to 2. Give me like an exact number. I said it would be nice. It wouldn't be a long decimal. It wouldn't be irrational or anything. So what is it? Okay, again, I encourage you to pause the video and ponder because I'm about to spoil the answer. Okay, here it is. The answer is 2. Okay. The blue area is the same as the red area. Exactly. It's not 1.9999999. You know, it's actually equal to 2. When you continue this process infinitely of adding little squares on to all the little line segments, you literally get an area of 2. It fills out the entire diamond, I could say. Okay. So that's where these things come into play, right? Initially, those were gaps, and you might have thought, okay, those gaps might stay there, and I'll have some negative space that doesn't get added into the total. But actually, you know, there were those 4 little squares that went in there. And then if I continued it again, I would have, you know, like 16 or maybe 20, I forget the number, squares that go inside there. And it would actually fill in that entire gap. And the same is true for all the other gaps. It fills in literally everywhere. Okay, so that's my fun Thanksgiving problem. I'm going to continue and show you guys how you do that mathematically. But you don't have to watch. I think it's cool. But yeah, it's fine if you don't want to write it out with me. Okay, so let me erase some of this. And then start an argument why 2 is actually the correct answer. And you guys know enough in your like calculus education to understand this argument. So I think it's a good one to learn. Okay. The argument goes a little something like this. The area of the first square was 1. Right? We started with this 1 by 1 square. So of course the area is 1. But then I added on 4 smaller squares. Okay, so I added on 4 things. And those 4 things each had some smaller area. And I wrote it down over here, but we may not remember that these side lengths were 1/3. Right, so 1/3 times 1/3 is a 9th. So I had 4 of those. And then in the next stage, I added even more things on. Okay, what I added on, it may be tricky to think about. Let me just draw one of these side lengths. So I'm just copying like one of these things over. What we did was we added 5 shapes. There was 5 little squares we tacked on here. And if the black length was initially 1/3, then each of those lengths was 1/9. Okay, so I added 5 times 1/9 squared, we'll say. because 1/9 times 1/9 gives me the area of a little square. And I had 5 of those. But I actually had more than 5. I had that times 4, because this was just one side of my snowflake. There are 4 of them. So I'll multiply that number by 4. So 4 times 5 times 1/9 squared. Okay, and then I'll just tell you what the next term is. Again, I had 4 sides to the snowflake, and then I had 25 things I was adding. And the area of each square would have been, here, let me write this a little differently. It would have been, did I write that correctly before? Yeah, I think it's 1/9 to the 4th power. Okay, dot, 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 we continue to infinity. Hopefully that's correct. I think it is. The argument being, well, the side length of my square in this stage was 1/9. And so, okay, this side length was 1/9, meaning this side length is 1/3 of that. And, okay, maybe I made a small mistake. Let me double check. So that was 1/9 squared. And so, yep, that would be 1/27. So I guess that would have been, yeah, okay, let me correct this. All right, so that is 1/27 squared. Cool, my mistake. Okay, and we continue that process forever. Great. Okay, one thing you guys know is if you have a pattern like this, and I would argue this is a pattern, even though it's kind of complicated, you can write it. Okay, I'm not going to write 1 using this pattern, but I think everything else I can include in the pattern. You can write it using sigma notation. And I'm going to say n goes from something to infinity. Okay, and I'll keep little blanks here for what I'm trying to fill in. In each of these, I have 4 times something, because there were 4 sides to my snowflake. So I'll put a 4 times, and it looks like in each of these I have 5 to a power, right? This is 5 to the first power. This is 5 to the second power. 5 to the 1, 5 to the 2. And I could make an argument that there's a 5 to the 0 hiding here, because 5 to the 0 is 1. Okay, so we'll say that's 5 to the something power, 5 to the question mark. All right, and then in each of these cases, I have 1/something squared. Okay, and keep in mind I left the initial 1 out front because I don't think I could use the pattern for that. Next question is what goes in these question mark spots? So let's think about it. Let's say I picked, let's pick a value of n first, so the base of this sigma notation. And we'll think for a while. You could kind of pick anything, but picking something nice would be a good start. So I could say, yeah, let's say that goes from n equals 2. Okay, so I'll use black. So we'll start with 2. Okay, and I want this thing then to align with this. So this first term then is what I'm claiming is the n equals 2 term. And so 5 to the 0 should appear here. Okay, so 5 to the 0 I could write as 5 to the n minus 2. Right, so convince yourself that's correct. If I plug in n equals 2 here, I get 2 minus 2, which is 0. So 5 to the 0. And convince yourself it would work for the next term as well. So this is the n equals 3 term. And if I plug in 3, I get 5 to the 1. Okay, so that works. Now let's continue that and figure out what I can do for this final question mark. Okay, that is going to require a tiny bit of work. What I could do is I could think, well, let me erase something really quick. Just make some room up here. What I could think is, erase some more. This initial 1/9 was actually 1/3 squared. Okay, and maybe then you start to see a pattern where this is 1/3, 1/9, 1/27 squared. And so they're all powers of 3, right? This is 3 to the 1. This is 1/3 squared. This is 1/3 cubed. And so how do I make that line up with my, okay, starting with n equals 2, that would be 3 to the n minus 1 power. Because again, this term is my n equals 2 term. 2 times 1 is 1, so that's 1/3 to the first power. And it works for the others as well. Okay, so we've successfully written out a summation in sigma notation for the blue area, right? This is literally the entire blue area. We just have to figure out how to evaluate that sum. It's kind of tough because there's an infinity at the top, but we'll give it a shot. Okay, apologies for the jump cut. I had to go handle my baguette dough. It's now doing its second rise. Okay, so this is where we were. I had to redraw it because I ended Zoom and I couldn't bring it back up. So here's everything. And my goal is going to be to try to simplify this expression as much as I can, okay? Because even I admit it's pretty complicated right now. The first thing I'm going to do is I'm going to bring this 4 out front. I can do that because 4 does not depend on the index n. So it's the same if I were to multiply 4 times each of these terms and then add them up, as if I were to add up all these terms and then multiply 4. Okay, so this is the same as 1 plus 4 times the sum of everything else that was in here. Okay, next up, I'm going to write this term a little differently. Okay, so let me copy down the rest of the terms. 5 to the n minus 2. Okay, I claim this is the same as 1/9 to the n minus 1. Hopefully you guys can figure out why that is. I'll make a little sidebar down here and just say squaring a fraction is the same as squaring both the numerator, well, 1 squared is 1, and the denominator separately. And then rules of exponents say I should multiply those two things together. But multiplication is commutative, so I could actually swap the order they're in without changing anything. You may not have seen that before, but that's a clever trick that you're allowed to do. And then I know 3 squared is 9, so that gets me to here, which is what I wrote here. Okay, so let's erase that sidebar. Hopefully that convinced you that what I did is totally fine. The next step is going to be, I would really like these exponents to be the same. 1's n minus 2, 1's n minus 1. But I can make them the same by messing around a bit. In particular, I could pull a 1/5 out, and that would leave me with 5 to the n minus 1. And I'm not touching the stuff in parentheses. Okay, it may take a little bit of convincing to get you to agree with me that that's allowed, but again, we'll do a sidebar. 1/5 times 5 to the n minus 1 is the same as 5 to the minus 1 times 5 to the n minus 1. 1/5 is the same as 5 to the minus 1. And then if I add those exponents, I get 5 to the n minus 2. So this whole thing is the same as that whole thing. Okay, again, I'll erase my sidebar. So hopefully that's okay. Same story, how I brought up the 4 out, I can bring the 1/5 out. because the 1/5 doesn't have any ends on it. So really, just to save space, I'm gonna just put the 1/5 out here, so make it 4/5, and then erase the 1/5 from there. Let me rewrite this though, so that'll be 4/5. Okay. And then the nice thing here is these indices are the same. So, okay, sidebar again. I could write that piece as a single fraction. That's 5 to the n minus 1 over 9 to the n minus 1. And that's the same as 5 over 9 all to the n minus 1, since they have the same exponent. Okay, so maybe take a second to convince yourself of that, but I'm going to go ahead and put that in. And actually, again, to save space, I'll just combine them. So 5/9 to the n minus 1 is going to go here. Okay, feel free to go back in the video if you missed anything. Going a little quick. Okay, my final step is going to be related to the index on this summation. And instead of starting at n equals 2, I'm going to start at n equals 1. But to do that, I have to change something. Of course, I'm saying these two things are equal, so I really don't want to change anything. I just want to write it in a way that will look different, but give me the same answer. The same as like multiplying by 1 or something. Okay, so how do I do that? Well, originally, my sum started at n equals 2. And so this exponent, well, if n equals 2, that means that's 2 minus 1, which is 1. Okay, so the exponent of my first term in this sum should be 1. So now if I change my index to 1, I can put an n here. And so if I were to plug in n equals 1, well, that's just the first power. So in both of these cases, whether n is 2 and I subtract 1, or n starts at 1 and I just write n, the terms of my sum are going to be the same. Okay, and you could write those out in detail if you wanted to, but it's not just the first term that would agree, all the terms would agree. Okay, so I'm just doing that because it's a little nicer to work with. And now I have a big question about what that's equal to. And again, if you think about this, it's like saying, what is 5/9 plus 25 over 81 plus 125 over 729? And you keep going. And you want to say it's infinity. But according to this argument over here, it should be some finite number. Right? If the shape stays bounded within a diamond, the sum, which represents the area, should also stay bounded. It should be less than some finite number. It should not grow to infinity. Okay, so let's figure out what that is. I'm going to go ahead and erase some of my work just to clear up some space. So up here, I'm just going to copy what I had. It's 1 plus 4/5 of the sum, 5/9 to the n power, where n goes from 1 to infinity. Okay, last chance to look at it. I'm erasing the work below that point. Okay, and Zoom likes to erase a giant chunk of my screen until it catches up, but okay, there we go. Good to go. So I'm just going to figure out what that chunk is. Once I figure out that chunk, we'll plug it in and finish evaluating. Okay. So sum, I'm going to call it S just to give it a name. So S is the sum from n equals 1 to infinity of 5/9 to the nth power. And like I was saying out loud, we could write that out. I could say, okay, for the n equals 1 term, I get 5 over 9 to the 1, so just 5/9. For the n equals 2 term, I get 5 squared over 9 squared, just 25 over 81. And then for the n equals 3 term, I get, well, these get big very quickly, but that's 729. Okay, so that's what that sum looks like. I want to actually figure out S as a number, figure out what that sum evaluates to. And to do that, you have to think a little bit. It's not trivial, but it's this was one of the first beautiful results I saw in math. Not this particular problem, but a sum of this form kind of blew my mind. How on earth would you figure out what that is analytically? Like, write down an exact answer. So maybe you want to think for a minute. So feel free to pause. But if you just want to go ahead, then that's fine. One thing we could do is we could say, what happens if I multiply S by 5/9? Okay, because 5/9 is like the common ratio here that I keep multiplying by. So what if I multiply the whole sum by that? Let's see what happens. 5/9 of S would be, okay, I'm not going to write out the sum with the sigma notation, but I'll write it out here. That would be just 5/9 times each of these terms in this sum, right? Okay, so let's write that out. 5/9 times 5/9 is 25 over 81. 5/9 times 25 over 81. Okay, well, let's work that out. 5 times 25 is 125. 9 times 81 is 729. Okay, and I could keep going, but the numbers get really big. So let me erase this little note. And maybe you notice something here. This term, the first term here, matches up with the second term here. The second term here matches up with the third term here. And that would continue forever. They would always match up. And so what would happen if I slid this over, right? Imagine taking this whole thing, sliding it over like one chunk, okay, just so it's all lined up. So let me show you what that looks like. So I'm sliding it over. So everything that's equal lines up. Trust me, it continues when you go to infinity. And now you might think, I have a system of equations. I have S equals this, 5/9 S equals this. What can you do in systems of equations? You can subtract them, right? I could subtract this whole thing. It would be the same as doing S minus 5/9 S. Okay. So what does that get me? Well, S minus 5/9 of S equals, okay, 5/9 doesn't have a term associated with it, so that hangs around. Then 25/81 minus itself is 0. This minus this is 0. Everything is 0. It's literally just 5/9. Okay, so that doesn't tell me what S is, but that tells me S minus 5/9 S is 5/9. And now I can bring that all together, okay? That implies, well, what is S minus 5/9 S? It's 4/9 S, right? They're like terms. I can combine them. 1 minus 5/9 is 4/9. So 4/9 S equals 5/9. Solve for S. So S equals, well, multiply by the reciprocal, right? So multiply by 9/4. The 9's cancel, and that's 5/4. So what I'm claiming, right, just to reorient ourselves, is that S, this thing, is literally equal to 5/4. If I were to add up all these numbers to infinity and beyond, I would get 5/4, 1.25, exactly, on the nose. No different, right? Everything I did here was simple algebra. And yet, I get an infinite sum that equals a finite number. Okay, that's absurd. But I know that since this equals this, and that was the thing I was trying to find here, I can just go ahead, plug 5/4 in there, see what happens. So work that out for yourself. It's gonna be astonishing. But this equals, okay, I'm gonna write out the whole thing now. 1 plus 4/5, and that sum was 5/4. 4/5 times 5/4 is 1. That sum equals 2. Okay, what does that mean? Well, before we had this argument that this red diamond shape here, if we filled it in, that's basically a square turned on its side with side length square root of 2. So the area there was square root of 2 times square root of 2, which was 2. And the idea was our blue area, the snowflake, is something that's inside the red area. So it's some area less than or equal to 2. This shows that the blue area is literally equal to 2, not less than it, but equal. Which means, if you think about it in the geometric way, the snowflake fills up the diamond. If you continue to infinity, they're one and the same. That every gap here, for example, like this area was a gap, and this area was a gap, and this was a gap, and that was a gap. Every gap gets filled in by some little square, and some little square, and some little square, which is especially weird for these like triangular bits on the border, right? It's almost implying you can take infinitely many squares and get a triangle, which is true. I mean, we kind of just showed it. But yeah, you got that the area of the square Koch snowflake is literally 2. That if you take infinitely many squares and do this iterative process, you get a diamond, which is a square. So the square Koch snowflake is square at every iteration, and it's square in the limit. Its area is 2. Cool. This whole process, by the way, these are called geometric series for good reason, right? You can see it's a geometric argument that holds it up. So that is one of my favorite problems to go over in this kind of course. Once you've seen summations and you know enough algebra to deal with the headache of the sigma notation and then making it look nice and working out all the details. But I think it's a truly elegant problem. Hopefully you do as well. And I hope you guys have a good Thanksgiving. All right. I'll see you all next week. Take care.